Good afternoon, and welcome to the Alumni Reunion. My name is Greg Jameson. I am the Interim Chair of Mechanical and Industrial Engineering in the Faculty of Applied Science and Engineering. And we are so happy to welcome you today for our annual Stress-Free Degree Lecture Series. Before we begin, I wish to acknowledge the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home of many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. The Stress-Free Degree Lecture Series provides a great opportunity to learn from some of our leading professors on important and current topics without having to do the homework. So today I'm very pleased to welcome you and to introduce Professor Kevin Golovin and his talk, How Sustainable Are Your Surfaces? So Kevin Golovin is an assistant professor in the Department of Mechanical and Industrial Engineering. His research investigates interfacial mechanics, coatings, surface modification, and sustainable methods for achieving solid and liquid repellency. Professor Golovin is an inventor on 11 patents and the recipient of various accolades, including the Eco Innovation Case Competition Grand Prize from outdoor apparel company Patagonia. He was also named an emerging leader in chemical engineering by the Canadian Society of Chemistry. And I will add, subsequent to this introduction being penned, he was also named the School of Graduate Studies Early Career Advising Award winner this year. So congratulations to Kevin for that. So please join me in welcoming Kevin.
Good afternoon, everyone. Thank you, Greg, for the introduction. So today I am going to be talking to you about the surfaces that exist in your everyday life and how sustainable they may be. And I know this is supposed to be a stress-free lecture. There will be some topics here that may stress you out a little bit. I will try to bring that around and offer suggestions and things that are being done here at the university that will hopefully relieve some of that stress. That is the hope, at least. So there's really two topics I'm going to talk about today. One you may have heard of in the news. It's this concept of these forever chemicals. What are they? Why do we use them? Why have they been so difficult to remove from our daily lives? And what we're doing here at the university to quantify how much they're actually interacting with us as humans, as well as what we can do to replace them. And then the second topic I will talk about are microplastics that are coming from our apparel, at least the synthetic ones, and how we can eliminate the microfibers that shed from our everyday clothing, strategies to do that, and what is being done here at the university. So I'm going to start off with a material that you've probably heard of in your everyday life. That is Teflon. The chemical name is polytetrafluoroethylene, but you probably know it as Teflon. And this is a material that was invented almost 100 years ago. It was sort of discovered by accident when they were trying to make better refrigerants, and they accidentally made this white waxy substance that turned out to be this material that is quite ubiquitous in our everyday lives today. Some properties you may or may not already know about Teflon. It's quite slippery. It's hydrophobic, so water does not interact with it well. It is insulative, both electrically and thermally. It has this very cool property. Does anyone know what auxetic means? It's a cool little term. So the company Gore, which you may know of from Gore-Tex, was the first one to discover that if you take a piece of Teflon, you heat it up close to its melting point, but not quite there, and then you pull on it. If you imagine what would happen if you pull on a rubber band, it kind of shrinks in the middle, right? Teflon, when you pull on it, actually expands. And that's a property known as auxetic. Very few materials have that property. What happens, it goes from a dense material to a porous one. And that porosity is exactly what's inside Gore-Tex and allows for nice breathable membranes that happen to be made of Teflon. And also the thing I most want to talk about today is Teflon is chemically inert. Not much interacts with it. That's why it is useful for things like frying pans, chemical containers, wiring, and so forth. So the question that comes up naturally is then, is the use of Teflon sustainable? And for that, we kind of have to look at the structure of what Teflon looks like on a molecular level. Obviously, we're not chemists in here. I'm not a chemist either. I apologize if you are a chemist. So Teflon, if you look at its structure, only involves two atoms from the periodic table, carbon and fluorine in a very long chain. All polymers are chains when you look at them molecularly. You can think of it kind of as this very long, what I've drawn here as a snake with no head, so a snake with two tails. The reason I've drawn Teflon in this way is that when something happens to Teflon, let's say it's on your frying pan and you scrape too hard and part of it breaks off, you have some damage somewhere along that chain. And what that leads to is potentially something that could be dangerous. And I know I chose a cute little snake-looking thing here, but imagine that that's a poisonous snake, okay? That leads to a class of materials known as PFAS, perfluoroalkylated substances, essentially a Teflon chain with something at the end. And that something can vary, and there's about 5,000 different types, so I'm not going to go over all of them, but these are commonly referred to as PFAS, okay? And one way that PFAS exists in our world is that it is a degradation product of Teflon. So if you scrape your Teflon frying pan hard enough, it will come off. It is also actually a processing aid used when you produce Teflon. This is actually the problem in the 1950s and 60s when all frying pans were made of Teflon, the nonstick ones. People would heat them up too high, and if anyone had a pet bird, that bird would die. The reason for that was because this PFAS that was used to process Teflon got into the air, and birds are highly, highly sensitive to these chemicals. And so it was a literal canary in a coal mine type situation, and they figured out that those class of chemicals were coming out of Teflon frying pans. And that's why they tell you not to overheat your nonstick frying pans today. The other thing that this class of chemicals is used in, which is probably the most use, are lots and lots of other things. So if you recognize any of these things, food packaging, furniture, water repellent clothing, things that are in our daily lives, these PFAS chemicals are used everywhere. There's a study a few years ago about 1,400 classes of types of products that you might have in your home contain PFAS. You can also do really cool stuff with them, right? Make super water repellent shirts. And sadly, I had some pizza last night. It's on most pizza boxes. So it's basically everywhere because of all these properties. It's slippery, it's chemically inert, it's hydrophobic, it can repel things like grease. So that's all quite nice. The problem is, and the reason we get this name forever chemicals, is that same chemical inertness, so the reason why it's so attractive for all those properties, also means it doesn't break down in the environment, okay? And because of that, it ends up accumulating in things in the environment, such as water, that then animals and humans drink. And so it can be found basically everywhere on Earth, even places that you wouldn't expect to find it, such as the livers of polar bears or in remote mountain caps. Essentially, every place that scientists have looked, they have found PFAS in the natural world. In your blood right now, unfortunately, there's about 4 nanograms per liter of blood, and it will stay in there for about 5 years. That doesn't mean it's going to do anything health-wise to you, but I also don't think anyone consented to it being inside of your blood today, and so that's at the root of the problem. And I'm going to quickly go over this slide because this is a stress-free lecture. The PFAS can be bad for you, okay? Don't have to go into all of this, but that's the reason why we would like to replace it, okay? The other thing I want to bring up is that in the environment, it tends to focus places where it's fabricated or where it's used heavily, and that isn't necessarily evenly distributed across the world or even across Canada, okay? So places that make these type of products, that make PFAS or that heavily use it, tend to be close to neighborhoods and residences of lower income people, okay? So that has a major disparity in terms of Black, Indigenous, and people of color living in closer proximity than others. And when I was doing my PhD, which was in Michigan, we had a similar thing, which was going on in Flint. So this type of thing is called environmental racism, and it occurs mostly throughout the world, but even here in Canada, and it is a problem even with things like PFAS, okay? So just because you want the most waterproof jacket so that you don't get wet when you're going on your camping trip doesn't mean that someone else isn't suffering because of that. So it's a big problem, and especially for people in lower income households. You may be wondering, where does it actually occur most? In the United States, Everywhere where you see a blue dot here is where you can see major heightened PFAS in drinking water. There's also categories for military and just other. So it's found heavily in military places. It's used for firefighting. It's also used in aerospace applications, which is why it's near most military bases. Here in Canada, you essentially can map it very close to where humans live in Canada. And if we look specifically here in Ontario, one of the biggest places is near Pearson, but also near the Air Force Base. Okay? So it essentially exists around us, especially if you happen to live closer to the airport or closer to a military encampment of some sort. And the research coming out on this class of chemicals is not something that old, and more research is happening even today. So this year, there was a study that showed that if you eat freshwater fish, that's the equivalent of drinking water that contains PFAS for about a month. So if you like sushi or if you like seafood, you're ingesting a lot of these chemicals, even though you probably didn't agree to do that when you bought the seafood. And just this year, so Miriam Diamond is a professor here in environmental and earth science. She did an interesting study. They just went down to College Street and bought a bunch of food packaging takeout containers just from some of the restaurants on College Street, and then over 2 years measured how much PFAS would come off of those containers. And a lot came off, okay? And so she called this a regrettable substitution, switching from plastic to paper containers that have PFAS. The question becomes, do we really want to make that switch? We thought we were becoming more sustainable going from plastic to paper, but now we have these chemicals that are entering our body that we probably don't want in there, okay? Now, in terms of what can we do about this, and is this really as a recent trend as we thought, it actually is not something that is that new. So I have a little timeline here, and I don't expect you to read these, so I've blown up the important parts. So back in 1954, DuPont, who created Teflon, became aware that these PFAS chemicals were toxic, and that was actually the same year that someone put it on a frying pan. And just for nomenclature, so C8 is essentially the type of PFAS that is most toxic and was most used for many, many years, okay? But it's just one type of PFAS. It has 8 carbons long, and so that's why it's called C8, okay? And then in 1984, so DuPont already knows that C8 might be toxic, and then in 1984, they know it is toxic, but they decide that it's not economically viable to stop making it, okay? If you've seen the movie Dark Waters, this is essentially what that movie is about. If not, I would recommend it. It's on all your streaming platforms. So they know it's toxic, but they don't want to do anything about it. You'll see why that is in a second. Now, DuPont's biggest competitor is 3M. They, nicely for the world, decided to stop making C8 in 2000. And they actually warned everyone at DuPont that you may end up getting sued later because of your decisions. And that did happen. And in 2005, then, DuPont settled the class action lawsuit for about $250 million because of all that they did with their PFAS decision making. How much do you think PFAS gains them in business a year, though? It's about $1 billion a year. So you can see why they made that economic decision, even though now we're all suffering because of it. Now, luckily, all of that is the stress part. The stress-free part, okay, begins here. So in 2015, the EPA, Canada, the EU banned the use of the C8 chemical. Okay, so that's good. It no longer is available except for research. And what everyone did was switch to a different chemical called C6. Basically, instead of 8 carbons, went down to 6. But at least we've gotten rid of the most toxic one in theory. Okay? And in 2016, other countries joined on. And in 2023, so this year, hopefully, all the manufacturers have agreed to stop using this replacement chemical. Because, surprise, surprise, that one's just as toxic. In fact, potentially more toxic because it doesn't work as well as C8, so they have to use more of it. So not great. Now, even more stress-free, or at least hopeful, is that there is legislation right now, particularly in the EU and California, to ban anything with a carbon-fluorine bond, which may be going a little bit overboard. But their idea is, let's start off banning everything, and then if anything can prove that it is non-toxic, we'll allow that to be made. So that legislation is being discussed right now. If it passes, that's going to be a big, big change for the world, potentially a good one, but it's not as clear-cut necessarily as you would think. And I will point out there's no action yet on anything that already exists. Remember, these last forever, so banning new products and new production is good. There's no legislation on anything that exists today. Now, why I say that this isn't necessarily as clear-cut as you would think, here's one example. This is a picture that you may or may not understand what's going on, but this is basically the recycling of an EV battery for a car. Now, why am I putting that up there? Because it contains PFAS. Batteries contain PFAS. If you remove PFAS from allowing to be used in production, that includes in electric vehicles. And what that means is your electric vehicles will become much less efficient. So the question is, which is better for the environment? Using PFAS in a battery so that we can get rid of fossil fuel-driven cars, or getting rid of PFAS because it itself is hazardous? There's no clear answer right now, okay? This is what keeps us engineers busy. And so that's a good thing for me, less so for the rest of the world. Okay, so what can we do about it? And this is some of the work that my group and others here at the U of T have been working on to try and have a solution for these type of chemicals, okay? And we start with chemistry, and luckily for us, because again, we're not chemists, we ask the question, okay, if PFAS is very hydrophobic, what can we replace it with? What other hydrophobic things just exist in nature, or at least on the periodic table? And it turns out that's a very simple question to answer because there's not many things, okay? So we have all the fluorinated stuff, so here's all the nasty things that will be banned, and then there's really only two other options. Things like polyethylene and polypropylene, so your hydrophobic plastics, and then things like wax and silicones, okay? So it's really just those four things, and those happen to take advantage of, rather than CF2 or CF3 bonds, they have CH2 and CH3 bonds. And so we have a very small subset to play around with, and the use of wax is actually not a new idea, okay? You probably know that water and oil, which wax is the solid version of oil, don't mix. This is something the ancient Egyptians knew. They would plank their boats together, and then they would cover it with a waxy resin so that they would make it waterproof. If you just want to repel water, wax is the perfect solution. There's really no reason to look further. Some companies are doing that. If all you need to repel is water, make something hydrophobic, you can just use wax. The real challenge is repelling other liquids. And this is actually why PFAS is so prevalent, is it was thought to be unique in that it could repel other things, particularly repel oils. Now you might wonder why you would want to repel oils. We will get to that. But this property of being oleophobic, oleo is the Greek word for oil, was thought to be unique to fluorinated compounds like PFAS, and so there was no alternatives. And you can actually go into the literature and look on how do you make these other chemistries, silicones and waxes, repel oil, and they agree that there's no oleophobicity unless you fluorinate it, which kind of defeats the purpose, okay? So that leaves humanity with a choice. We can either go PFAS-free, we can have oil repellency, we can't really choose both. So that's how we started in this whole project, and it's not quite true, what I've put up there, and you can actually go back into the literature. You have to go far back, to the 1940s, before Teflon became famous, and scientists had actually found other chemicals that exhibited oleophobicity. Now, I don't expect you to know what icosal alcohol is. It doesn't really matter what it is. The point is, it's not fluorinated. So there is at least a chance for other things to repel oil. And so that brings me to my favorite chemical, which is, or favorite material, I guess I should say, which is silicone. You probably know this material in your daily life, perhaps in your kitchen or on the back of your cell phone. It exists as a rubber, as a solid. You may also know it if you like splurging a little and putting synthetic motor oil into your car. Synthetic motor oil is basically silicone oil. So it exists naturally as a liquid. It also is in almost every cosmetic product that exists, and lotion. You also may know it as a sort of curable resin. It's used in most movie prosthetics, or if you do any house repairs like I have to do daily, then it's caulking and silicone for edges of your windows and whatnot. Okay? The reason why I bring this material up is because we think it's the replacement for PFAS. Now, what I'm showing here, this is actually a movie from Amy Bilton's lab over in mechanical engineering. This is oil being spilled into water, and then she's developed a little fibrous mat that is coated with silicone, and she uses it not to repel oil, but to absorb it. It actually works really, really well. It can soak 90% or 90 times its own weight. So for oil spill cleanups, silicone just absorbs a ton of oil. So my idea that it can repel oil seems maybe like not a great one. What you're actually seeing there, so silicone as a just pure material is a liquid. So the synthetic motor oil that goes in your car. If you want to turn it into a rubber, like your kitchen spatulas, you have to take, if you remember the snake molecule, that's how all polymers look like, you have to connect them with little knots. Those are called chemical crosslinks. What happens when silicone is in contact with an oil is it swells, like a sponge with water. Okay? And that's what's happening with Amy Bilton's sponge there, and it works really well to clean up oils. And again, if it's not cross-linked like this, if it's not a rubber, it just exists as lots of these snake chains all coiled up. And when it gets in contact with oil, they mix together, like water and alcohol. So we had the idea of a different structure, one that hadn't been tried out before. And that is something that we call a brush. So you take a chain of this silicone, and you attach it to a surface, but only at the very end. And if you put them densely on the surface, our idea is that the oil has nowhere to go. And so it has to sit on top, and this is what we would call repellency of that oil. And it turns out that that works. Okay? So what you're seeing in these videos, I guess I'll play them both, play them all at once, is droplets of various liquids being repelled by these silicone brushes. And it works really well. Here's a droplet of fluorinated oil. These are actually the hardest oil to repel. Just sliding along on one of these silicone brushes. And they do that just because there is nowhere else for the oil to go, and so it gets shifted above. Okay? You can do more fun liquids, such as bitumen. Everyone knows what bitumen is? So the roads you drove in on, if you drove, the black stuff that holds the asphalt together is bitumen. It's a byproduct of petroleum. It's very, very sticky. It's what makes roads smell kind of bad. You can also repel those. Big use for the petroleum industry. You can also do mud. And I put, or toilets. I don't have a video for toilets, but you can kind of imagine what that would look like. But here's the mud version of that. So that could be useful to reduce the amount of water that a toilet uses. Or we're working with a bicycle company that doesn't want their BMX bikes to get covered with mud. So you could use these silicone brushes to do that. I'll give you two examples of things we've done in our lab specifically. One I talked about already, food packaging. So grease resistance is the main reason why all these PFAS chemicals are used on food packaging. You'll notice things like donuts, pizza, French fry containers. They're all very greasy. And if you've ever had a French fry container that doesn't have the PFAS in it, your hands probably get greasy and you don't like that. So there's a benefit to this. And right now, all of these use this C6 PFAS, the one that in theory will be phased out by the end of this year. But again, companies don't have a replacement for it right now. And so Xiao, he's a postdoc in my group. He's been working on this and trying to use these silicone brushes in that nice morphology as a replacement for grease-resistant food packaging, but without the PFAS. So what I'm going to show in this video, you remember that it's the structure of those brushes that's important. So siliconized paper actually already exists in the market today. Does anyone know the common name for siliconized paper? Parchment paper, yes, good. So you might use parchment paper already. And so what we're going to do here is compare parchment paper, which is on the right, to, so the chemical name of silicone is PDMS. So that's what those are on the left. And you'll see here you put a drop of this grease mimic, and both of them repel it nicely. But then when you try and take the grease away, it soaks into the siliconized. So the only difference there, chemically these are identical. The structure of those silicones is quite different. So we're working on that with this company, Paper Excellence, out in BC. And the other thing that everyone always asks, so I like to put it here, if you try and recycle this paper, you still can't. The reason for that is not because silicone is recyclable. Technically, it isn't. But the thickness of this layer, you remember, we're talking about single molecules, so it's about 4 nanometers. Tiny, tiny thickness. So the amount that isn't recyclable, basically, you can't even detect. So you can completely repulp and reuse the paper. The other area that we've been working on for a number of years, so this is in collaboration with Arc'teryx, the outdoor jacket company. They have been using the C6 for a while and have known for years that they want to get away from it. And right now, all their jackets use C6. So Sadaf, who's a PhD student about to graduate, has been working on making a replacement for C6 for fabrics. And this is what at least one of Arc'teryx's liner fabrics, so this would be a mid-liner in between your shell fabric of a jacket and the layer that touches your skin, or your shirt that you're wearing under the jacket. So what Sadaf has figured out is you can put these silicone brushes on the fabric, but it's a bit more tricky because now we don't have a flat surface. Right now, this is a very complicated structure. We have a woven textile. Each of these weaves also has fibers within it. It becomes a very complicated thing. When she coats it, the structure of the fabric doesn't really change. But she came up with this mathematical model that obviously I'm not going to go through. The point is that what everyone thought before she had started this work was that you could not repel oils on fabrics unless you used these fluorinated compounds. Okay? What she found is the fluorinated compounds work best, which was expected, but the non-fluorinated ones, particularly silicones and waxes, still work, just not as well. Okay? You have to design that chemistry correctly, but they still work. And so what you can see here are droplets of oils, sweat, water, but also some common oils that are being repelled by this fabric. So what you're looking at is the world's first oil-repellent non-fluorinated jacket, or at least fabric for a jacket. And right now we are working to commercialize this with Arc'teryx. Scale up is quite challenging just because it has to be very, very durable. You don't, the worst thing you want is a jacket that loses its water repellency over time, and so the consumer gives it away or buys a new jacket, and the environmental footprint of creating 2 jackets, way worse than the PFAS or whatever the coating material is. Okay? So that's been a challenge, but that's what we're at today. So those are two examples. There's a number of other areas where PFAS is used, right? Thousands, about 1,400 different categories. And I won't go over all of them today. But the ones I put up here, I put up for a reason. And that reason is you'll notice there's a lot of green tech on this slide, right? Photovoltaic cells, wind turbines, greenhouses. The challenge is not necessarily replacing these chemicals because you can find a replacement. We think these silicone brushes are. But the challenge is a lot of these technologies are in a lot of countries' 2030 or 2050 targets for carbon emissions and whatnot. And if you take away PFAS, all of those technologies change, right? If we can't recycle our lithium-ion batteries or we have to change our lithium-ion batteries because our cathodes are now illegal, that's going to change all of our targets. So it's a complicated, complicated thing, but also makes for fun research, keeps my students busy, okay? I want to switch now, what I say, from pans to pants. So shift more into the idea of textiles and specifically this emerging issue of microplastics. And you may have heard of microplastics in the news or microfibers. I'll go over what that means in a second. So I'll start off with fast fashion. You may be aware of this. But essentially, in the last few years, the amount of clothing that people are buying has increased, but the amount of times that they wear it before they buy a new garment has decreased. So we're producing more clothing and wearing it less. And you may not know that the carbon coming from the textile industry is worse than aviation and shipping combined. And you probably think about the greenhouse emissions maybe when you take a flight. You may not think about it when you buy a shirt, right? But it's actually worse. And part of that is because of fast fashion, when you have apparel that is no longer in style, routinely it's burned, right? You can't do anything with it, so you just burn it. And in addition, about 20% of wastewater comes from just dyeing textiles because we like things in pretty colors. That's okay. Now, microfibers, or microplastics from textiles, are just one of the emissions that I'm going to talk about today. And essentially, every time you wash your clothes, or even as you're wearing it today, small bits of fiber come off. And if your clothing is synthetic, that's a small piece of plastic. Okay? So if you're wearing polyester, nylon, spandex, that's a small piece of plastic that doesn't degrade. Okay? If you wash your clothing, hopefully you do, each piece releases about 700,000 microplastics every time you wash it. And because of that, about a third of all the plastic in the ocean actually comes from textiles. You may think it's water bottles, right, that's covering up the ocean, but it's actually textiles. And again, if this was not bad for humans or anything, I wouldn't really bring it up. So it has some health effects. The main ways in which it enters us as humans are three ways. So we either drink it in water, we consume marine animals or plants that uptake the plastics, or you actually breathe it in the air. Okay? And I'm going to touch on how we can fix maybe two of those today. I bring up this. So there's an organization called the Microfiber Consortium that figured out that this is a big problem, and they want to do something about it. This is not like Teflon. This is not PFAS that was known since 1938 to be hazardous. You'll notice that this initiated 2 years ago. Okay? So this really is a new issue that people have come up with, and I don't expect you to read anything on here. I don't think I can read it either. The point is, this is a very new issue, and hopefully by 2030, some things can be done about it. But this whole microfiber consortium is built on the idea that we need to raise awareness of the problem. And I teach a class on green engineering, and we would define this as what we call infant environmentalism. It's kind of like stages of grief for recognizing you have a problem. The first stage is to accept that you have the problem. So that's infant environmentalism. One step further, some countries have adopted. So France has decided that by 2025, all the washing machines that are sold in France should have a filter that collects these microfibers so that they don't enter into the water. And Australia has said so as well by 2030. California and actually Ontario are also considering it. They haven't come to a decision yet. But the idea is that if we put a filter on our washing machines, then we'll collect all these fibers and they won't enter the ocean. Now, I will say, if you've ever cleaned out your lint trap of your dryer, you probably just throw it away. That trash enters the landfill. That then enters the water. So it may just delay the problem. There's no guarantee that this actually solves anything, but it's a Band-Aid solution and everything helps these days. And that would be what we would define as adolescent environmentalism. Okay, so this is an end-of-pipe solution. We're still creating the emissions, but at least we put a Band-Aid on it. Now, Chelsea Rockman, so she's also here in environmental and earth science, actually tried this out in Parry Sound a few years ago. So small community here in Ontario, and they put a filter on about 1 in 10 people's homes. 97 washing machines all had filters, and they were able to capture billions of microfibers. Okay? And this is what they look like in the filter or under a microscope. And so it really does help in terms of capturing the microfibers. If we did this here in Ontario, we'd capture 100 trillion microfibers every year. But again, then what do you do with the microfibers? If you toss them, they end up in the water. If you burn them, you've got emissions. So I think it's a good idea. Is it the full idea? Possibly not. The other thing I would point out, so that's if we treat water, okay? So potentially you can stop microfibers or delay them getting into the ocean, getting into fish. But what about the air? Turns out, and this is sort of very recent research, that just as many microfibers are released into the air when you're wearing your clothes as when you wash it. And a filter on a washing machine is not going to do anything about that. And if you're wondering, since I've been talking, I've probably breathed in about 100 microfibers so far. And you're probably breathing in 5 per minute. And so these end-of-pipe solutions can't really mitigate the crisis. Maybe they can slow it down, but not really fix it completely. And so we had the question 2 years ago, what can we do about this? And we actually had a more simple question of why do fabrics shed microfibers at all? And it seemed like something that was fairly obvious, or at least our first guess turned out to be the right one, is that when they're in the washing machine, they're rubbing against one another, they're rubbing against the washing machine, that's where they break off from. So it has to do with this rubbing friction. And because we're a surface group, we can measure friction. So what we did is we took a ball of nylon, rubbed it on a disc of nylon. That's sort of a standard friction measurement test. And you can see, this is where sort of the ball rubs against the nylon, that you can damage nylon with itself. That's not really anything special. You can also measure how much friction nylon has with itself. This is the same coefficient of friction that if you remember from your basic science class, you have a brick sliding down an inclined surface, coefficient of friction, exact same thing. Happens to be a value of around 0.25. What's more important is that you can see the damage when you do that. So if you take a textile and wash it, you can see actually the bundles of fibers start getting broken and torn up and fibrillated into smaller pieces. And so we wanted to see if we could fix that. And first we had to do a method of quantifying microfibers. This is the exact same way that Chelsea Rockman's group does it. We do it in a lab. You basically, rather than a whole washing machine, you do a little lab scale version of a washing machine where you wash your textile, you filter it out, you collect all the fibers that come from the filter, and then you count them one at a time. That's where undergrads are very, very useful because their eyes are so sharp, okay? And you'll see the numbers here. It's good to have lots of undergrads. So our idea was that if we reduce the friction on the fabric using those silicone brushes, they happen to have low friction, we might reduce the amount of microfibers that come off the fabric. Does that work? No, not at all. So when you wash nylon, this is after I think 9 washes, you get about 4,000 microfibers per gram of fabric, okay? And that's why, again, undergrad's very useful. That's a lot of microfibers. When you put low friction, so those silicone brushes on, you get about 3,000-ish, but statistically, the same amount, okay? Why was that happening? It turns out that washing your clothing is quite an abrasive process, and if the coating's not durable enough, so if those silicone brushes aren't durable enough, you start off with low friction, and then as you wash or as you abrade, you end up with the same coefficient of friction as the untreated nylon. So basically, the coating was coming off, okay? And that's why it didn't further reduce the microfiber. So it may have reduced, and then coating came off, and then stopped working, okay? So postdoc of mine, Shadeep, he had this idea. When you're coating a wall, or when you're painting a wall, if you want to increase the adhesion of your paint, you put on a primer layer first, right? And what that does is it chemically connects the wall to your paint. So we had the idea, why don't we do the same thing, but on a molecular level with our coating, and that would increase the durability of our low-friction silicone brushes using a molecular primer. And Shadeep had this idea that in the textile industry, when you dye your clothing, if you do it correctly, that doesn't come off in the wash. So if we can mimic that type of durability, we should be able to have something that stays during washing. And it turns out that dyes are applied to textiles using ionic bonding, so it's an electrostatic effect. And so he came up with a version of attaching our silicone brushes using an electrostatic effect to nylon. Now, does that work? Well, first we tested just that primer, okay? This is a molecule I won't go over, but it doesn't work because it's not a low-friction molecule. It's just the primer layer, so same amount of microfibers. And then we also had the idea of testing fabric softener, because that is essentially the liquid version of silicone that people put in their clothing, in their laundry to make it nice and soft and fluffy. It would be great if that reduced microfibers, but it doesn't, okay? So really what you need is the combination of these two, right? The primer, which chemically bonds our low-friction layer, and the low-friction layer at the surface, and then you get this drastic reduction in the amount of microfibers that sit on the surface, about 95% reduction. You can also see that after washing, the fibers essentially look fine, okay? You can also see it in the amount of microfibers you collect. There's essentially a lot less. If you go back to our original idea that it's all about friction, you can also see that when you have this low-friction nylon that has the primer, it exhibits low friction, and that low friction stays there over time, okay? The fibers also, when they are washed, get rough and start to be damaged. So if you measure the roughness of the fibers before and after washing, it goes up. If you measure on the fibers before and after washing, it stays the same. And you can see that under SEM. Has a nice little textured surface after washing, so it's starting to get damaged. When it's coated and has that low friction layer, nice and smooth. And so you can almost eliminate, almost completely, we're working on getting to 100%, probably we'll never get there perfectly, the microfibers from a textile by putting low friction coating, okay? we're trying to scale this up so that by the end of 2023, we'll have a product that is either available for people or most likely for companies that they will put on their apparel. I most likely am going to assume that Patagonia is going to be our first adopter just because they sort of gave their company to the environment last year and are very interested in reducing microfibers amongst other things. Okay? And this would be an example of what is called adult environmentalism, where you actually go and you fix the problem. Okay? Not a Band-Aid solution, not just identifying that you have a problem, but you actually go and try and stop it in the first place. Okay? Now, that was just for nylon. So obviously, there's still other fabrics to work on, polyester, spandex. The hardest thing is actually fiber blends, because coming up with a primer that works for multiple different fabrics is challenging. You basically need good chemists. If you know any, let me know. Also, I showed that it worked in laundering, but remember, half the microfibers come out in air. So we're still working on figuring out, does this low friction coating also work when you have your fabrics just existing in the air and rubbing as you wear them and move around? Also, the type of low friction layer, we've done it with silicone brushes because we like that technology. There are lots of other low friction materials that exist. There's actually work out of Italy that shows that potentially pectin, the stuff that's the pulp in your orange juice, works quite well, at least initially, to reduce microfibers. If you could make it robust enough, maybe that would be a good solution. And then there's probably the most important things of actual legislation and stuff trying to cap the emissions of the textile industry so that companies actually have to stop having textiles that emit microfibers in the first place. Okay? So in closing, this is more of a plug for surfaces in general, because I'm a surface guy. Emissions are released from a source to the environment, whether it's CO2, whether it's microfibers, PFAS. And if they're released from a source, that source has a surface. So surfaces are very important to control and potentially affect the emitters and our world. And one thing that at least DuPont and the PFAS story teach us is that we can't really look at short-term benefits if we want to be sustainable and think about the long-term health of ourselves, our planet, our children, and whatnot. And then I always like to bring up that these social issues, you can't really separate those from the environmental issues because people live in locations. And those are inseparable from engineering issues that we like to solve. Okay? And with that, I'm going to thank my group. You saw work from these 5 amazing people, but everyone helps out in their own way. We call ourselves the Durable Repellent Engineering Advanced Materials, or DREAM Lab, so this is the DREAM team. And you saw some work today that was sponsored by Arc'teryx and Lululemon and the Institute for Water Innovation here at U of T. And with that, I'd be happy to take any questions. Thank you. I don't know who's deciding on who gets to ask a question. Okay. I've been told to wait until the mic is there because it's being recorded.
So is cotton the best product to buy and wear?
Ooh, so interesting question. In general, natural fibers are better than synthetic fibers, but natural fibers doesn't mean that they have no chemicals that have been added to them. Once you have enough chemical additives in the cotton, they essentially act just like a synthetic textile. So yes and no.
How would you know?
Oh, it's very difficult. So there is a company called BlueSign, and they work with a lot of the BlueSign with the apparel industry, and they monitor every single chemical that goes into a piece of clothing, and you can track it all the way to its source. So if you buy something that's BlueSign certified, they at least can tell you what's in it, so you know you're making an informed purchase.
Blue sign?
BlueSign, yes,
Okay.
Correct.
Thank you.
Yep.
That was wonderful, but are we sure this isn't a regrettable substitution? Specifically, what's the environmental fate of the silicone?
So silicone is a very good environmental and, more importantly, human health material. So you may know silicone is used inside the human body for certain people. So it is biologically inert, and it is created from sand, and you can break it down with acid. So those 3 things that you can generate it from the most abundant material on the earth, sand, You can break it down easily, so it doesn't last for thousands and thousands of years, and it doesn't do anything to the human body. I would argue that it's not a regrettable solution.
But specifically, if we're not recycling it and it does get out, what's the environmental fate? How long does it last?
It depends on the silicone. So the ones we are generating, there's basically no research on that because they're so small. Larger silicones, their environmental fate is essentially like the larger pieces of plastic that end up in humans, where they are ingested, but they are inert inside the body, and then they're just released. So they don't accumulate inside the human body. And that's about the best I could tell you right now. But good question, yeah.
Okay, thanks. It's slightly off topic, but would you be able to work on a glue for labels that when after you peel it, that glue comes off easily, like say on glass jars? And
So I hate that, right? When there's the residue, because you have to get 100% of the residue
Can you work
off.
on making a glue like that?
It's not something we're actively working on, but it's an interesting idea. So adhesives are also one of the big reasons that a lot of paper products or just products in general become not recyclable or not sustainable.
Because it makes the jars reusable easily.
Yeah. So it's an interesting idea. Maybe we should talk more. Yeah. Other questions? I think we have one.
The microfibers that could be collected in the washing machine and you're saying would go to landfill, is anybody thinking or working on how to recycle those?
Recycle them. So not specifically recycle, but deal with, I guess is a better word for it. So if you take certain plastics and burn them for energy, they have a net positive effect on the environment. So people have looked into using them to create energy, not necessarily recycle them, like into another textile.
What happens to PFAS when you microwave the containers?
Ooh, so nothing basically. And again, this is one of the reasons why it's so challenging and why it accumulates, because it doesn't break down easily. If we could just break down PFAS with microwave, that would be very nice, and then it wouldn't be a problem, but we can't. Yeah.
Hi. There's more plastic in the 7 seas than there is fish. You're on a schematic door to a universal discovery, you and your colleagues. You mentioned briefly plastic filters on washing machines, and as you know, plastics make a bacteria, and a bacteria makes of edible food. So you have wooden fruit and vegetable insulation and pectin towards zero emissions of the watchdog of 2040.
Is there a question in there?
Yeah. Give away your brilliant schematic door to this universal discovery of getting rid of all the plastics in the 7 seas.
I'm
not just
sure.
by plastic filters.
Yeah, I'm not sure that what we've discovered will fix that problem. So by adding these coatings to the fabrics, you prevent the microfibers from coming off textiles in the first place, so that they just remain intact. But they don't do anything for cleanup. What's in the ocean stays in the ocean. We have colleagues in mechanical and other departments here that are working on environmental remediation and cleanup to remove the plastic from the 7 seas. But what we're working on is sort of an earlier stage where you prevent it from coming off in the first place.
I can see their sustenance and the appetite. I can see your quagmire that you're not going to eliminate, even with the zero emissions dagger that the protocol that was set forth. So of course, you're not going to eliminate all the plastics in the 7 Cs.
No, and that would be difficult, but if you can at least slow down the amount that's entering it, I think that would be a net positive, right? So that's sort of with that work, that's our ultimate goal, is to stop having more being added to the oceans. But good question, yeah.
I think I heard that there is some research that's being done in Japan where they're using fungi to try to break down plastics. Have you heard anything about that?
Yes, and for specific plastics, there are specific organisms, in some cases fungi, in some cases bacteria, that can break down certain plastics. I'd say it's an infant technology today, and it's very plastic specific because you essentially teach the organism to break down one type of chemical bond. But I think it basically is the future in terms of potentially recycling and degrading plastics, yeah.
Sorry, this is not gone a different direction, but I also heard, and I don't know if this is myth, if you wash your laundry in cold water,
Is
they
better.
said that you'd get
Yes.
less microplastics. Okay.
Yes, you generate more microfibers when you wash with hot water. And these days, detergents have been engineered well enough that hot water doesn't really make your clothes cleaner. Like, unless you're washing without detergent, which would be strange. If you have detergent, wash with tap water, cold tap water, yeah. Okay, we probably have time for one more question. Oh, we got one down here. I'm just giving you exercise, yeah.
I have a quick question. So you were talking about pans, like nonstick frying pans and stuff. So if you have one that's starting to wear out, you know how you said if you buy more clothing, you're causing more damage? Are you creating more damage or more PFAS by continuously using one that's starting to wear out? Or are you better off just replacing it? Because I'm going to keep using my nonstick pans. So
That's a good question. I'm not sure I've seen a study compare, like the full life cycle assessment of frying pans and whether or not you should replace it. I would suggest buying a non-PFAS frying pan, though. I don't want to advocate for a single brand, but there are brands available that are non-stick, that essentially use a similar technology to these silicone brushes that have no fluorinated anything. I replaced all my pans a few years ago, so yeah, that would be my recommendation for health reasons. Yeah. So I think we're out of time, and I guess Greg will come back and say a few words.
Thank you very much, Kevin.
Thank you.
I wanted to reflect on a couple of things in Kevin's talk. One is, and he only paused on this for a period of time, but the emphasis on equity. And I think one of the things that our alumni might be pleased to hear is that in engineering, which is perhaps not a place where you might imagine that equity is a focal topic, in fact, it is increasingly so. And so that I was really pleased to hear Kevin point that out. We have many faculty members, including Amy Bilton, who he mentioned, who are directly concerned with how engineering solutions and engineering processes directly pertain or interact with equity considerations. So that's great. I wanted to let Kevin know, so the example of spraying your camping gear so that you don't go wet, I was telling him about doing that this morning to my camping gear. On my deck. At least I did it outside, I was thinking, so it wasn't like inside breathing it. But I am pleased to report to you that after you got talking, I looked up the product that I was using, and it is a non-chlorofluorocarbon product. I'm not a chemical engineer. And it specifically says that, and it uses some other technology. So I felt a little bit relieved. But the last thing that I wanted to share with you was that Kevin's award that I mentioned, the School of Graduate Studies had just given him an award for supervision of graduate students. That's not for supervision of undergraduate students. I'm a little bit concerned about what you're doing with your undergraduate students, Kevin. So I think maybe when I get back from Norway, we can talk about that a little bit, okay? Just want to finish by thanking all of our alumni for continuing to be part of the University of Toronto community and for being here, for sharing your questions, for sharing your ideas. It sounds like maybe you have a collaboration opportunity in the front row. It's just, we are a community of ideas, and so it's so wonderful to hear you, to see you here today, to listen to some of these ideas and to share your own ideas. So thank you very much for being part of our community.